All right, picture this. It's the early 1990s. The computing world is basically defined by these dim, gritty workspaces and glowing green CRT monitors. The whole industry was entirely dependent on the CPU, but those general-purpose processors, they were struggling heavily to render complex 3D graphics in real time. It's in this incredibly high-stakes, constrained environment that an ambitious startup decided to make an existential gamble. Survival not guaranteed? Honestly, that wasn't just some dramatic catchphrase. It was their daily reality. You see, long before this company became the undisputed titan powering the modern artificial intelligence revolution, NVIDIA was just a cash-strapped startup founded in 1993. They had extremely limited resources, totally uncertain customer demand, and were facing a brutally competitive semiconductor market. At one point, they were roughly 30 days away from bankruptcy. Think about that. Survival, not dominance, was their absolute focus.
And man, survival almost didn't happen. Back in those early days, you had these exhausted engineers dealing with the near-death experience of their very first chip, the NV1. It used this unconventional architecture that the market ultimately just rejected, leading to plummeting financial charts and a critical burn rate. But actually, this failure defined CEO Jensen Huang's leadership philosophy. Confront your failures honestly, abandon unsuccessful ideas quickly, and pivot rapidly to survive. That exact pivot led to the Riva 128, which literally saved the company.
Welcome to today's Explainer, where we're unpacking the rise of NVIDIA. Today, we're going to trace the cinematic, heavily engineered journey of how a struggling 1990s hardware company managed to architect the infrastructure for the modern intelligence era. It is a crazy story of relentless focus, brilliant strategic pivots, and the immense power of parallel computing. Chapter 1: The Graphics Crucible.
Over 3 decades of relentless hardware transformation, this company evolved at breakneck speed. We start way back in 1993 with that NV1 chip, but the real breakthrough came in 1999 with the release of the GeForce 256. NVIDIA didn't just improve PC gaming with this chip, they established the very concept of the modern GPU. From pixels to possibilities, this continuous, relentless pursuit of acceleration laid the groundwork for everything that followed, culminating in the massive, highly complex Blackwell architecture we see today.
Chapter 2: The Parallel Computing Pivot.
So this technical pivot, it fundamentally changed computing forever. Think of traditional CPU sequential execution like having a few incredibly smart workers who can only do one complex task at a time. It takes minutes or even hours to get through a heavy queue. But GPU parallel execution uses thousands of simpler cores doing thousands of things all at once. NVIDIA realized that the massive math required to render 3D pixels could actually be repurposed for general-purpose computing. The GPU was uniquely and perfectly built for immense scale.
But here's the thing, hardware alone just wasn't enough. In 2006, they launched their ultimate secret weapon, CUDA. This platform completely bridged the critical gap between hardware and software. By allowing developers to program these massively parallel GPUs using familiar languages like C, CUDA effectively unlocked the GPU for science, healthcare, and advanced analytics. Hardware makes it possible, sure, but software makes it genuinely useful.
And just look at what happened next. Today, the global CUDA ecosystem includes over 4 million registered developers and thousands of real-world applications. By building this immense, robust software platform and sticking with it year after year, NVIDIA locked in deep developer loyalty. They essentially created an insurmountable strategic moat, years, even decades before the AI boom ever started.
Chapter 3: The AI Awakening. Then, in 2012, something magical happened. It was the AlexNet breakthrough. Researchers shockingly used standard NVIDIA gaming GPUs to train deep neural networks, conquering a massive computer vision competition and changing the industry forever. From that exact moment on, we see a massive leap forward. Transformers take over in 2017, ChatGPT brings it mainstream in 2022, and now we're rapidly entering the era of multimodal AI and massive interconnected AI factories.
So, what was the financial result of that awakening? A staggering $79.8 billion in revenue for the year 2024 alone. I mean, wow. This number totally illustrates the monumental financial explosion generated by the generative AI boom and the sudden global ubiquity of transformer models. Because their hardware was already uniquely built for parallel processing, NVIDIA seamlessly transitioned from a graphics company to the absolute engine of the entire AI era. But what is actually happening behind that massive revenue? Let's break down the millisecond by millisecond journey of a single human prompt.
From the user's question, it gets broken down into smaller mathematical puzzle pieces called tokens, translated into numbers in a process called embedding, and sent into massive transformer layers. Billions, literally billions, of parallel calculations are happening across thousands of interconnected GPUs to generate an intelligent response in less than 1,000 milliseconds. It feels totally instantaneous to us, but it is entirely built on massive, synchronized parallelism.
Chapter 4. The Intelligence Infrastructure.
Just wrap your head around the sheer complexity of the Blackwell architecture. We're talking high-bandwidth memory, interposers, NVLink interconnects pushing 1.8 terabytes per second, and highly advanced chiplet packaging. NVIDIA is no longer just selling a single chip anymore. They are building and selling a highly complex, interconnected computing engine designed specifically to handle the staggering demands of trillion-parameter AI models.
Because of this, NVIDIA now views data centers entirely differently. They actually call them AI factories. These vast, integrated systems, equipped with autonomous robotics and massive data streams, exist for one purpose: to transform raw electrical power and data into trained intelligence. The factory itself has literally become the computer.
And this whole factory concept, it has rapidly gone global. The world is now illuminated by an immense network of cloud providers: Microsoft, Amazon, Google, Meta, all building unprecedented computing networks atop this very hardware. Hyperscale cloud providers have essentially turned this silicon into the foundational bedrock of modern technological progress, connecting the entire globe to a single intelligence infrastructure.
Chapter 5. The Future and Its Risks.
Now let's dive into the headwinds here, because the future isn't guaranteed for anyone. First off, there is a stormy mountain of risks. We're talking intense market execution pressure, complex supply chain constraints, and volatile geopolitical tension over where these chips can even be exported. But perhaps the biggest physical hurdle is exponential energy demand. Every AI breakthrough requires more compute, and compute requires massive amounts of power. Data centers run 24/7, and by 2026, a single large AI facility could demand gigawatts of power. Powering this immense growth sustainably is an incredibly complex challenge.
Furthermore, they are right smack in the middle of what we call the great AI race. Tech giants are competing aggressively across every single layer of the AI stack, from foundational models all the way down to the physical infrastructure. And while NVIDIA currently powers the acceleration layer, powerful rivals and major cloud providers are heavily investing to break their dependency. They're developing their own custom silicon and specialized accelerators. The landscape out there is incredibly volatile.
Yet, even with these immense risks, the ultimate goal remains absolutely staggering. The ambition goes way beyond consumer chatbots. The Blackwell architecture and its future successors are aimed at accelerating human potential across our most vital, life-saving industries. We are talking about faster drug discovery and healthcare, smarter precision manufacturing, radically safer autonomous transportation, and highly optimized clean energy grids. The aim is to empower humanity to solve its absolute hardest scientific and medical problems.
This growing global ecosystem really reflects the company's true legacy. They didn't just build a successful graphics card, they became the foundational architect of the accelerated computing era. From digital twins perfectly simulating reality to autonomous robotics shaping our physical world, the intelligence they help generate is powering the next profound era of human achievement.
Which leaves us with this final, incredibly profound question. Can we build a better world with intelligent machines? You know, the challenge isn't just about making faster chips anymore. It's about the immense global responsibility that comes with powering the world's intelligence. Think about that as we move into this next technological frontier. Thank you so much for joining me for this explainer, and I'll see you next time.